morning, everyone. This webinar is called Introduction to Process Water Recycling and Treatment in Mineral Processing, and it is part of EIT Breakit Learning Project. My name is Saara Hagnes. I started my career in Outotec as a process metallurgist in a ferroalloys business line about 7 years ago. For the past 4 years, I have worked as a product manager in the industrial water treatment side. Looking briefly through today's agenda. First, we will look at the water and its role in the mineral processing. Then we will move over the fundamentals, looking to the beneficiation process called flotation process itself. After that, we go through some factors that are affecting water quality, followed by looking at how the water quality impacts on a flotation process. Then we have some test results, 2 example cases, which I will present. Then looking through Outotec solution to problems that water quality may have to flotation performance. Then we go to the water assessment workflow, where we describe how we actually approach the problem. Finally, we will end the webinar with the conclusions and Q&A session. Here we see the big picture where water is present in minerals processing. This is sort of a mind-side-wise approach of a picture. Apart from the process plant site, there are several water sources and flows within the site itself. This is a conventional tailings dam approach, where we are using conventional tailings management. As you can see, a lot of water flows are around the tailings dam, because the tailings dam is the place where a lot of water is lost due to being bound to the tailings itself, released in evaporation or seepages. So in the case of a conventional tailings dam, more raw water is needed as an intake. So in order to secure the operation in the plant, some water storage would be good to have, for example the dam, as in this case, and also some process water reservoir. The water from the tailings dam can be recycled back to use to plant as a process water, because the water quality is quite often in a good level. Other option is to discharge water to environment, which normally requires some water purification to follow the environment regulation for the discharge. Of course, this depends on the site where we are. Water is needed in several places in mineral processing plants. It has many functions. It is not just a medium for wet beneficiation, but it is also a very valuable resource. It can also be a cost item, especially in the water scarce, dry regions. So water needs to be considered as reagents with an OPEX associated with it, not just as a processing media. But most importantly, the quality of water will affect production efficiency and recovery. Water is also connected to the whole hydrologic water cycle of the area and is impacted by weather conditions, where water evaporation and seepage in conventional tailings is a major concern. Water is also a source of a risk, not only operational, but also environmental, could be reputational, for example, in the case of the tailings dam bridge. There could be also some financial risks, for example, difficulties in getting insurances. This picture is looking more of the process level approach of the plant. This is a generic processing chain of mineral processing. As you can see, there are several water sources. You can see all the blue lines presenting water. For the water management point of view, the best idea for the processing plants is to treat the water in the specific unit processes and recycle water internally, instead of having large volumes of water to be treated in the end. It is important to capture the water from the dewatering especially important in water scarce areas. In order to have enough water available for processing, the best idea for saving the water is to recycle, where overflow of the clarifiers and thickeners are captured from the dewatering and put back to the process for use. Looking through some factors that are affecting mineral processing performance. One is, of course, the mineralogy of the ore. What is its chemistry, its crystal structure, and physical properties? In mineral processing, we need to know what is the composition on the mineral surface, also what is the floatability of other minerals on the particle, its grindability, etc. Another factor affecting mineral processing performance are equipment, how we have dimensioned those, how we use those. Do we, for example, under or overgrind the concentrate? We know that some overgrinding of the ore easily produces fines in the process, and this can then disturb the process performance in the following separation processes in froth flotation. The way we select the process chemicals affects the process performance. We know that there are differences between chemicals, how they work in cold temperatures. Of course, dosing affects as well. Then there can be some residual chemicals present in the recycled process waters that can have an impact on the process performance, and those need to be taken into account. Naturally, the way the plant is operated affects the performance, but also water has a significant impact on process performance, the quality and quantity of it. So what is flotation? In brief, flotation is a separation method where the fine-grained minerals are separated from each other. The aim of flotation is to modify some of the surfaces so that the valuable part can be recovered in a concentrated form. Apart from reverse flotation, the surfaces of valuable minerals are treated with chemicals so that they are hydrophobic and remain unwetted and will this way adhere to air bubbles. The valuable minerals are then lifted in a flotation cell where they enter the froth. The froth containing these particles can then be removed. Unwanted minerals that naturally resist wetting may be treated so that their surfaces will be wetted and they will sink. So now going to the factors that are affecting water. One factor is the tailings management, or the way we are managing the tailings. In conventional tailings, the retention time can be 30 to 60 days, which allows some chemi-biological reactions in the tailings dam. Also, degradation, especially of organic molecules by UV radiation, is enabled. All this combined with long sedimentation time is expected to clean the water enough so that it can be reused in a processing plant. Then when we start to recycle more water and turn more towards paste or even dry stack tailings, the retention times get shorter. It's typically around 4 to 8 hours. The reactions that were possible in the conventional tailings dam don't have time to take place, and impurities can start to accumulate in recycled process water. Seasonal variations have their impact on water quality as well as the temperature changes. In lower temperature, kinetics gets lower, viscosity of froth increases. Quite often also consumption of chemicals is increased. Looking at these three different factors in detail, here we have a case of a copper concentrate that produces 20 million tons of copper per annum. The conventional tailings management picture is presented on top of the slide and the water tailings below it. You can see that the input water need for the raw water is around 1,200 cubic meters per hour in the copper concentrator. This is mainly because of the water that is locked up in the tailings area, as you can see in top of the picture. Also, the seepage and losses through evaporation affect the raw water needed. If we then look the filtered tailings on the bottom of the picture, you can see that the raw water needed is much lower, only 300 cubic meters per hour. So obviously we are saving water when using this kind of tailings management. In this approach, we are using high rate thickener and filter approach, so effectively dry stack tailings. We are recovering more water in the dewatering step instead of just having the tailings area and the losses. The lock-up water is much lower. We have only 320 cubic meters per hour. Also, seepage is reduced, so really the losses of water are much lower in terms of water quantity. Another point here, however, is that the quality of water could be worsened and accumulation of impurities can take place. Other than the tailings, accumulation of impurities in the case of recycling water is another important point. So, when we are closing the loops, for example, due to the tailings management, impurities can start to accumulate. This picture illustrates how the accumulation of impurities like residual reagents, sulfur species, metals, organics, and also biological activity increase the more we close the water loops. Process becomes unstable along the accumulated impurities, while the water parameters such as pH, temperature, conductivity, and reduction potential change. All these can have adverse effects on the flotation process. Seasonal variations also have a significant impact on water quality as the temperature changes. Presence of humic substances in raw water changes depending on the time of the year. There are variations in microbiological activity depending on the circumstances, such as nutrition level, pH, and temperature in water. In low temperature, the dissolution of reagents is lower and their consumption increases. Reagents as well nitrogen compounds coming from explosive are food for the bacteria, and increase of these components in water accelerates microbiological activity. High microbiological activity can then be seen as algae blooming and slime formation, which can have a detrimental effect on flotation process. Temperature and pH variations in the water have impact on the evaporation occurrence, as well as on the precipitation dissolution rates of different components. In lower temperature, the flotation froth can overstabilize, causing problems in flotation. You can see the graph on bottom of the slide where you can see there's some differences in recovery between summer and winter. The recovery is much lower compared to summer. There are several components that can be accumulated in recycled processed water and therefore harm the flotation performance. Here are the most critical ones: fines, ions, and residual reagents presented in these blue bubbles. Firstly, fines. And when we are talking about fines, we consider under 20 micron size of silicates, talc, clay, organic material. So what we know about the impact of fines in recycled water is that they have a large surface area, which increases flotation chemical consumption. Also, selectivity tends to decrease with the increase of fines. In some contents, fines with opposite surface potential will attach to valuable mineral surfaces and this way prevent collectors to attach. But ions, we know that some ions can depress or adhere on the surface of valuable mineral and this way prevent absorption of collector on the surface of mineral particles. If the pH is favorable for precipitation, some ions may precipitate and disturb the flotation process. For example, gypsum formation between calcium and sulfate ions. Gypsum will precipitate on finely grinded mineral, and this way blocking the site where collector can attach. Gold flotation, you see the ore here on top left. Gold flotation is very sensitive for fines and ions, especially calcium ions, which can depress free gold. Also, cyanides have been noticed to depress gold flotation by increasing the solubility of metal xanthates and preventing absorption of collector on the surface of mineral particles. You see the phosphate ore below the gold ore. So in apatite flotation, calcium ions can react with the collector and reduce its concentration for flotation, and this leads to declined apatite recovery. Also, phosphate ions have a strong depressant effect on apatite particles. Studies also show that some bacteria in the process water can interact with calcium-containing minerals and cause strong flocculation. This results in reduced floatability and decreased selectivity, leading to decreased flotation recovery. Silicates and precipitated iron hydroxide found in the water loops are increasing the viscosity, and this way the usage of flotation chemicals in iron flotation. Then the last group of residual reagents. Presence of residual reagents in the process water may cause bulk flotation, which compromises selectivity. And then, for example, residuals of CMC reagent, carboxyl methylcellulose, in process water can cause microbiological growth and also unwanted depression and recovery decrease. And even though we now have listed few problem makers and their effects on flotation performance, it has to be kept in mind that the impact of these components can be very complex, and in dynamic flotation environment there can be several components affecting and also repelling each other in some situations. Here we have a case example of studying the water quality impact in process water in nickel flotation. In this study, we performed flotation tests using 3 different quality waters: process water containing 10 ppm of a collector chemical called xanthate and 500 ppm of fines. Then the other water was treated, filtered process water, and as a reference also tap water was used. As you see, the results show that the process water without any purification gave the lowest recovery, around 10% nickel recovery. It is the brown curve in the graph. Then when you look at the blue curve in the graph, it is the recovery curve of the treated water. We see that with the treated process water that had less fines, we achieved already about 17% of a nickel recovery. So there's a significant difference between the recoveries. Well, naturally, tap water gave the best results, the green curve in the graph, but this graph just illustrates how water quality has an impact on the flotation recovery. And with a relatively simple water treatment, we achieved significant recovery increase compared to the process water without any treatment. Another case example here is from the study of zinc flotation process, where some free cyanide affects negatively on the flotation performance. Cyanide complexes the copper used as activator for zinc. And in addition to that, cyanide itself has depressive effect on sulfide minerals. The used detoxification method is the iron cyanide precipitation process, which is made with ferrous sulfate. However, it has been observed that the detox process is not working well because free cyanide is found out to be present in flotation waters still. So in this study, several flotation tests with different water qualities were performed. The primary focus of the flotation tests was to improve zinc flotation by destructing cyanide. The results of test work were clear. Current detoxification process doesn't perform well due to low dosing rate of ferrous sulfate and high operating pH. The method of ferrous sulfate detoxification is recommended to be replaced by more efficient detoxification. The red curve in the recovery and grade graphs shows the flotation results with the current detoxification process, having the recovery about 81% and grade seems to be 34%. The best zinc flotation results were achieved with complete cyanide destruction by strong oxidation with hydrogen peroxide, the curve presented in yellow. In the best zinc Rafa flotation test, recovery was about 92% with a grade of 24% of zinc. Required copper sulfate amount to float zinc was drastically reduced to 1/6 of its original amount after the process water was treated with hydrogen peroxide. The green curve presents the flotation results after water treatment with ferric sulfate, and we can see that also that method gave relatively good results in flotation, with the recovery being 83% and grade 32. Aeration of the processed water before the current detoxification seemed to improve zinc flotation only slightly, as you can see in the blue curve, having the recovery about 50%. Should be noticed that the samples in this study were collected on different days, which means that there are some differences in the head grades, and therefore tests are not fully comparable to each other. But nevertheless, it can be noted that hydrogen peroxide treatment is the best and most effective method for removing free cyanide from processed water. This is according to flotation results. It is likely that the grade of zinc to concentrate could be improved. However, flotation reagent optimization was not included in this test work. Outotec processed water recycling plant is our Outotec optimized solution to stabilize or even improve the process performance when the earlier mentioned accumulation of impurities, water seasonal changes, or the way tailings are managed are affecting to the production. The processed water recycling plant is mainly targeted for polymetallic, copper, gold, and iron reverse flotation concentrators. It is especially targeted for concentrator plants where the tailings are dewatered and the concentrator's water usage is changing to short cycle water streams. For these concentrators that have dewatered tailings, this solution works as a kidney, removing the accumulated substances from disturbing the process performance. This process water recycling plant consists of pre-designed and standard water treatment units for a wide range of volumes. The application-specific configuration of units is depending on the water quality requirements and can be designed according to specific customer needs. But the main idea of the solution is to produce the right water quality, meaning good enough water to right place. And then different water treatment units will be determined by the customer need. Here you see a few units it could be consisting of. There's a microflotation unit for removing main part of the solids, precipitation unit for removing dissolved impurities, and polishing filtering for higher reduction of chemical residuals. The most comprehensive way for mine water management is combining the water treatment solution with our online water quality and quantity called VQQM system. This enables predictive modeling of the water treatment needs. Through monitoring, uncontrolled quality and quantity variations of the process waters can be detected. The actual needs are mapped and process can be stabilized. The VQQM consists of wireless monitoring stations, online measurement sensors, data collection, dynamic water balance modeling, and a user interface with reporting service. Here's a typical water assessment, which is carried out through following steps. First step is the site inspection. In this step, we evaluate the core processes so that we can identify the problems or issues. This will help to set development targets and identify potential solutions. The second step is the water balance by process modeling. For the modeling, we have the Outotec HSC9 simulation tool, which is a fast tool for making the first estimates or simulations of full water site management impact on processes. Impurities in the water are analyzed to support the water balance simulation. The next step is then the testing. Laboratory or pilot scale testing will be conducted for verifying the simulated water treatment concept. And the fourth step is the development of concept for process water treatment, which is based on all the findings from the previous steps. The technical and economic feasibility of the concept is here evaluated with the concept proposal. And moving to conclusions. Water quality has a significant impact on process performance at mineral plants by affecting to production efficiency and recovery. That is why it should be considered more as a reagent and not just as processing media. Outotec process water recycling plant is developed for meet these challenges related to process water quality and quantity by producing right quality process water and high and stable process performance. Our water monitoring tool, water quality and quantity management, and simulation tools are supporting the water management and treatment offering in the mineral processing field. Thank you, and now there are some time for questions, possible questions. Okay, there were a few questions raised. One was how often customers ask such services from Outotec. Water-related services. Well, those questions come like weekly, so very often, but the scope and the need is always different. But water is becoming more and more important service in mineral processing. This is my opinion. The other question was that which metal extraction is very water consuming? I mean that the amount of water is that much and that cannot be recovered. Oh, good question. I think all the mines are interested to see what is the portion of the valuable portion of that ore, and they are making their calculation according to that. And well, I don't know, there are places in world like Chile which is lacking of water much, and I think the operation of those plants is somehow quite in a critical path. So I would be morely saying that this is a geographical question and not maybe related to certain metal extraction. And there was a question of about the nickel process. Are there any new methods to improve the recovery using with treated water? This is also a good question. New method to improve the recovery. Well, the recycle the process water, that's maybe somehow, I don't know, new thing, or the concentrator plants are now more and more start to recycle their waters, and now they start to realize, I mean, not only liquor concentrators, but maybe all, that the water quality has impact on all kind of flotation processes. So some way this is a new way of thinking. And new method, maybe new method in the water treatment sense, that there are new water treatment methods coming also from our side to be able to use this recycled process water without losing any production. Hopefully I answered your question. Is there any other questions? Okay, but then if not, then I wish you all have a nice day, and thank you for listening.